This video will provide a quick overview of constructive interference, destructive interference, and resonance, and will complete the note packet that was handed out in class on Wednesday, March 11th. Waves carry energy from one place to another, and when waves interact or interfere with one another, that energy can cause there to be a larger amplitude or a smaller amplitude for that wave. Remember, amplitude is the height of the wave from equilibrium. And so for constructive interference, it's going to construct or make the waves larger. So it's a good way to remember constructive interference. You add the amplitudes because you're building something. And so when waves 1 and 2, shown here, interact or are occupying the same space at the same time on a medium, it's going to add their amplitudes and you get a larger wave than you had before. I'll show you a quick video of superposition, constructive interference. This is a clip, so you'll see this blue wave on the top approaches this blue wave on the bottom, and when they reach the same space at the same time, you'll see the red is the sum of their amplitudes. So we'll watch that real quick. And as you can see, the amplitude adds, and then they pass through each other and keep going on their way. So let's watch that one more time. So the amplitudes add, and then the wave carries on its way. Notice how after they've passed through each other, that wave keeps going. So the energy stays with that wave. So like when they are in the same spot, amplitudes add, but then they pass through each other and they keep the energy they started with at the beginning and they keep going. So it's a little different from our collisions back in semester 1 when we were talking about momentum and we had our eggs and they splatted on the plywood or were safe with the sheet. It's not quite a collision like with solids. That energy passes through each other and continues on its way. And again, one of the places we see constructive interference used most often is with speaker systems. So at concerts, speaking engagements, even the PA system, the announcement system at school, by having sound waves come from multiple speakers and line up so that the crests and the troughs are in the same place at the same time can make the sound louder and louder, making things easier to hear. And so that's an example of constructive interference. Now the opposite of constructive interference is destructive interference. So when two waves, like our wave 1 here and wave 2 in blue, when they occupy the same space at the same time, as you can see, the waves no longer match up. When there's a crest, the highest point on this wave 1, there's a trough, the lowest point on wave 2. And so when you have a crest and a trough in the same place at the same time, those are going to cancel each other out and you end up with a wave with no amplitude at all. So for destructive interference, it's like you're destroying the wave, you're breaking it down, so you're subtracting the amplitude this time. And so we're going to look at this video clip of two waves with destructive interference. As you can see, this wave pulse, this singular wave, is above equilibrium. This one is below equilibrium. When they end up in the same place at the same time, remember the red shows what happens when those waves are combined. So right now, like they're independent waves, as they travel towards each other, you'll see them cancel out and then continue on their way. So one more time, they start to interact, and as they move through, we'll try to skip through this, so you can see when they're overlapping, you see it start to cancel out and that amplitude gets smaller and smaller and smaller until these two, the crest and the trough, are in the same place at the same time and you have no amplitude at all. And then as they pass through each other, we start to see that wave emerge below and above until they fully are separated and they are done interfering with one another. A real-world example of destructive interference would be noise-canceling headphones. So one of the big new things are AirPods and the noise cancellation versus transparency mode. So a lot of times when you have noise-canceling headphones, the headphones themselves emit a wavelength of sound at a certain frequency with a certain amplitude. And when that interacts with the sound waves that are all around you, when there's destructive interference, when those amplitudes cancel one another out, that cancels out the sound before it reaches your ear. And so when you have active noise cancellation mode, as Apple calls it, that's sending out a wave that's going to give you full destructive interference with certain background noises, background frequencies that are common that are all around you. Whereas transparency mode, it might be a little bit out, we call it out of phase, where the waves don't quite line up with each other, so you still get a little bit of amplitude even when those waves are in the same space at the same time, so things are quieter, but you can still hear some things that are going on around you. So if you use noise canceling headphones, I would definitely check out, there are many articles and resources about how exactly they work, but the big key is it's destructive interference. And just to give you a video example of what I mean when I say that there's not complete destructive interference, you can see that the shape of this wave here is more of a parabola, whereas this one is a little bit narrower in focus. They both have the same amplitude distance from equilibrium or the midline, but you'll see when they interact with each other, you can see how this second wave is being subtracted out of the first one. And so you can still have a sound wave or an earthquake wave or like any mechanical wave on a medium, and they'll interact with each other in this way, passing through each other, canceling out when it's destructive, adding when it's constructive. And so this is what happens when noises aren't fully canceled out. You can still have some sound because that amplitude is still there. The topic in this video is resonance. Now, resonance is the quality that all objects have. So everything vibrates at a natural frequency. So for example, if you tap a glass and that sound you hear, that sound, that note that you hear is its natural frequency that it vibrates at. So everything on Earth in the universe has a natural frequency. Now, when you drive something at that frequency, that means you make it shake at that frequency, then what's going to happen is the amplitude of the wave is going to get larger and larger and larger unless it's stopped by something like friction. Now, in the case of solids, that means that things can shatter and break. So things like a glass can break when it's caused to vibrate by something like your voice. And that can happen with earthquakes and other types of waves as well. So when you have that wave making something, the particles in something shake at their natural frequency, again, that amplitude will get bigger and bigger. And I have two examples posted in my MCPS classroom for you to look at related to resonance. The first one I want you to check out is the boy who breaks the wine glass with his voice. So when he is yelling at the glass, you'll see the straw move. The straw is there so that you can see that the glass is vibrating. Since glass is kind of transparent, it's kind of hard to see on the film. There is a bird in the background, but I do want you to try to listen to see if you can hear the note being given off by the glass. You can hear it echo after he stops shouting at the glass, and eventually the glass will break. The other example is the Tacoma Narrows bridge collapse that happened in 1940. This is a real bridge. It was made of steel and concrete, so these were solids. And due to the way that this bridge was constructed, the wind flowing over Puget Sound, which is in Washington State, caused the bridge to start to oscillate, to vibrate back and forth. And they called it Galloping Gertie because this went on for weeks, and eventually the amplitude got so large for the wave formed by this bridge moving in the wind that it eventually collapsed. So this is real footage. Remember, back in the day they made newsreels, so it'll seem like a movie, but this was all real footage captured in real time. So definitely check these two videos out. They're great examples of resonance and what happens when you cause something to vibrate at its resonant frequency. If you have any questions about constructive, destructive interference, or resonance, just let me know. You can shoot me an email. and I'll try to get back to you as soon as possible.